In this session, we are going to discuss about the second law, then the state function of entropy and applications of this entropy in the entropy change calculations for different elementary processes. So, you see after industrial revolution, what happened? The conversion of heat efficiently into work was one of the prime importance in this physics. Okay, in the domain of physics, this conversion of heat into work, and also in engineering, that was one of the fundamental question, and how efficiently it can be done, right? Generally, you see, this question actually leads to this second law and the property of entropy, the idea of heat engine and all, right? So, if I discuss from our school days, we have learned about the conversion of energy, and we know that energy from this elementary level can be converted into any other form with 100% efficiency. Yeah, it's correct, and heat can also be converted into work with 100% efficiency. There is no doubt about it. However, if I think of the continuous conversion of heat into work, then we must regain the initial state of the system periodically, right? Otherwise, the progressive change of the state cannot be actually, we cannot accommodate it in this continuous process of converting this heat into work, which is not possible, because we have started maybe from a high temperature, high pressure condition of a gas, say it's an elementary system, and the gas is expanding in a piston cylinder assembly producing work. So, whenever the gas expands, its pressure decreases, its temperature decreases, its volume increases. Now, if we go on allowing this change of the state, it's at some point it becomes impractical, because the pressure of the gas will be changing to atmospheric pressure, right? Now, if I want to extract further work, we have to create a vacuum environment in the surrounding, otherwise it is not possible. So, what we have to do, if it is a practical process we have to think of, then we have to regain the initial state of the system upon doing some work on that piston cylinder assembly and the gas enclosed in it. So, that is a kind of perpetual conversion of heat into work, and from science and engineering standpoint, we are more interested, or actually we are focusing on this specific issue where continually or perpetually we have to convert heat into work, right. So, you see this idea leads to that concept of the second law, which is a universal law and very important in checking the feasibility of every process. Like we all know that heat will always flow from high temperature to low temperature, and that is a natural process. So, the process whichever is natural, actually it is going to happen, and whatever we think, we may design a very integrated process, but first we have to check the feasibility of that process to happen, right. The feasibility means here whether the process is possible or not. How will you judge it? You have to judge it from the paradigm of second law. Okay? So, without going into the details of this qualitative discussion, if I now focus, pinpoint to that statement of the second law, there are two alternative statements, right. First, I will give the statement, and then we will elaborate about this statement. There are two statements, as you all know. One is the Kelvin-Planck statement, another is a Clausius statement, right. And we will discuss this device, what actually it's not being quoted in this law in toto, like heat engine and refrigerator. The first, that Kelvin-Planck statement is associated to the performance of heat engine, but the word heat engine does not appear explicitly in that statement. and whereas in the second statement, that is a Clausius statement, it is associated to the working principle of a refrigerator, but again the word refrigerator does not explicitly appear in that statement. So, what are the statements? So, first is the Kelvin Planck statement. You see, no apparatus can operate. I am just reading it out, try to we will next explain it. No apparatus can operate in such a way that its only effect, that statement or this phrase only effect is very important, and only effect in system and surrounding is to convert the heat absorbed by the system completely into work by the system, right. So, again I am reading it out. No apparatus can operate in such a way that its only effect in system and surrounding is to convert the heat absorbed by the system completely into work done by the system, right. So, we are thinking here actually the inherent statement is the periodicity or the cyclic process. Why? Because when a system is absorbing heat and simultaneously it is performing work, or sequentially it is performing work, then definitely there will be a change of state of that system, right. And whenever it is delivering that work into the surrounding, because it is performing work, automatically it will be delivered to the surrounding, there will be a change of state in the surrounding as well. Now, if the surrounding is indefinite, it is open, right. Surrounding itself is an open system, okay, and it is indefinite in mass. So, the effect is generally negligible. If I am performing some work, the work will be used up in doing something, but the change of state as it has got infinite mass is negligible. However, there is a change of state of the system, right, because when the system is absorbing heat and performing work, its elementary canonical properties like pressure, temperature and volume, they are going to change. However, that change is not permitted according to that statement of the second law. That means its only effect is to convert the heat absorbed completely into work. So, what does it mean? It has to, after intermittently, it has to regain its original state, right. So, definitely within intermittent change of state is permitted, but at the same time it must regain its original state. That means it must operate in a cyclic process. So, otherwise you see there are different thermodynamic processes, maybe with ideal gas, right, where the complete conversion of work into heat into work is possible. Now, here it is very imperative to note, it is quite imperative and important to note that conversion of work into heat, it is immaterial, because heat is not a usable form of energy, work is, right. So, from the engineering interest, we will always think of the conversion of heat into work and not work into heat, right. We have seen that in friction and any other processes, the work done can be converted fully into heat, right, if it is properly arranged. So, the thing is, there are a lot of thermodynamic processes which are non-cyclic. That means it is the work generation from heat is not the only effect, it is associated with a change of state, right. So, in those processes we can fully convert the heat absorbed into the work done by the system. The common example is the typical isothermal process where we are doing it with an ideal gas. You see, we have discussed it for isothermal process. With ideal gas, we have delta U equal to 0 as temperature is constant in isothermal process. So, Q is equal to W, right. So, whenever Q is equal to W, and we can write it as nRT into ln of V2 by V1. So, the thing is, here heat absorbed is completely converted into work. However, there is a change in state, because if the initial state is P1, V1 and T1, its final state is going to be P2, V2 and T1. Temperature will remain unchanged because it is isothermal. So, there is a change of state, and the only effect is not the conversion of heat into work. Additionally, there is a change of state, which is beyond the purview of the processes what is within the scope of second law or the Kelvin-Planck statement of the second law. Here only effect means it must be a cyclic process. So, the change of state in the surrounding, unless it is a system with a definite mass, we can discard it, because it is generally the environment, right, the atmosphere, etc., which has got m tending to infinity. So, if you are doing work, the change of state is negligibly or small or insignificant. So, under this condition, we have to only focus on the change of state of the system, right. So, here automatically we have to think of a system which converts, which takes heat from certain high temperature object or high temperature system. It must convert, if it operates in a cyclic process, it must convert a part of energy, part of the heat absorbed into work, right. It cannot do it to the full extent with 100% efficiency, and reject some amount of heat to another reservoir at low temperature. So, that is basically the idea of heat engine. We will actually discuss this principle of operation of the heat engine, but before that we have to think an equivalent, we have to generally cover this equivalent statement of the second law, which is with respect to another device called refrigerator. As you all know that in running a refrigerator, what we are doing actually, we are transferring heat from low temperature body, low temperature system to a high temperature system. So, it is not a natural process. Natural process will be following the direction of heat transfer from high temperature to low temperature. But when we are changing the direction of a natural process, we have to invest work in it, right. The external work must be supplied unhindered to the device, and then the device will operate in a cyclic process and will convert this or transfer this heat from low temperature object to the high temperature object, and that is the paradigm of Clausius statement. What is that? No process is possible without which consists solely, no process is possible which consists solely in transfer of heat from the one temperature level to a higher one, right. So, again it is the statement solely in the transfer of heat. Previously it matches with the equivalent with the only effect, right. So, here also the change of state is not allowed, it must operate in a cyclic process, it must do it continually, right. So, if I have to exhibit something or exhibit some some process continuously, I have to repeat that process again and again and again. So, we have to regenerate the state back, which means the obvious it must be obviously a cyclic process, otherwise it is not possible. So, with that understanding of the cyclic process, which is related to that only effect or the sole effect phrases of Kelvin-Planck statement and the Clausius statement respectively, we now go to this understanding of the basics, very basic schematic and the energy transfer operations in heat engine and refrigerator, which the idea of these two devices are inbuilt in this first and the second statement of second law. So, you see, what is a heat engine? Heat engine is a device which takes up heat from a high temperature reservoir, thermal reservoir. So, consists of two thermal reservoirs, one at high temperature and the other must be at a lower temperature. And this lower temperature reservoir universally in all heat engine, it is the atmosphere or environment rather, or rather let us say it is the atmosphere, right, where we discard that heat. Okay? Consists of two thermal reservoirs, one at high temperature, and thermal reservoirs, what are they? So, you have to understand what is a thermal reservoir. A system with MCP tending to infinity, such that if we add or abstract some finite amount of heat to and from the system, there will be no temperature change. We can understand the idea of thermal reservoir, and it is exactly consistent with the infinite mass or infinite water equivalent, that is MCP of atmosphere. But how come a high temperature reservoir be a thermal reservoir, classically a thermal reservoir where abstraction of heat, because from the high temperature reservoirs we are taking up heat, how come it is having a constant temperature? Because it must be finite mass. So, here in the practical examples are, here we are adding the same amount of heat what we are abstracting, right, and that means we have to burn fuels. Okay. So, the chemical change in the fuel actually, and because of this heat of reaction, it generates heat, and that is given to this thermal reservoir, and the amount is, we will think under steady state consideration, the amount what we abstract, the same amount is being supplied to the reservoir, and essentially its temperature remains constant, right. So, it may not be a reservoir or it may not be a system with infinite heat capacity. However, for a finite heat capacity, if I continuously supply the same amount of heat, right, upon burning fuel, and mostly it is a fossil fuel. So, if I go on supplying that same amount of heat, right, whatever we are abstracting, its temperature is evidently is going to be constant. So, even the high temperature object in this real life, we cannot think it classically in terms of classically matching with the definition of heat reservoirs, but actually by adopting some alternative process of supplying this abstracted heat, we can think it's equivalent to be a classical heat reservoir, even if with it's having of some finite MCP. So, anyway, so it consists of two thermal reservoirs, one at high temperature and another must be at lower temperature. Additionally, there must be a working material or working medium, like such as gas enclosed in piston cylinder assembly. This is the elementary example, and classical example that gas enclosed in a piston cylinder assembly may serve as a heat engine, right. So, what is a schematic? Schematic of heat engine we have high temperature reservoir, let us say at temperature TH, and this in thermodynamic jargon we call source. So, it delivers heat to the working medium, which is actually the heat engine. It produces some work and rejects the rest of the heat to a low temperature reservoir, which is generally the environment or atmosphere, right, which is at temperature Tc, and in thermodynamic jargon again we call it sink. So, here this is simply the schematic, and if I write the respective terms like heat input and the work output and the heat rejection, we generally it is better to write it with absolute values. Why? Because which one is our system we do not know what we are going to analyze, because there are actually three systems we can fragment overall heat engine. We can think it overall as a system, but we can fragment this heat high temperature reservoir, the source, as our system. So, in that case QH is negative, but alternatively if I think it in terms of this heat engine, this QH is positive. So, in a general form, a general schematic, it is better to represent it in terms of its absolute value, right. So, this amount of heat is given to that working medium, and this working medium is operating in a cyclic process. That means there is a change of state, and we are again returning back to the same initial state after some process is being executed. It may not be a single process like a single path going to that some specific state, and again I am returning to the initial state. It may be a multiple combinations of the processes, like whatever we have discussed, this isothermal, adiabatic, polytropic, isobaric, isochoric, etc. So, it may be a combination of that. So, with that it is producing some work, right, and this is the net work being produced. Why I am calling about, or I am talking about the net work? Because when I am trying to regain the original state of the system, I must do some work, right. So, the work which is being produced in work producing step, and the same working material is consuming some work also in work absorbing step in order to regain its original state. So, there must be a difference, right. So, this del W is actually work produced minus work intake, okay. So, we can write it like this. So, this is producing some work. However, it also has to reject, according to the second law statement, it has to reject some amount of heat to the cold reservoir. So, in a sense, if we can write the Kelvin Planck statement like, if mod QH and mod W they are greater than 0, then mod QC has to be greater than 0. So, this is basically the Kelvin Planck statement in simple form. Right? This is basically the Kelvin Planck statement. Now, how much amount of work is being produced and what is the conversion efficiency of this heat intake into work? That must be a performance rating parameter of this heat engine, and we call it efficiency. So, definitely you can understand that mod QH must be equal to mod W plus mod QC, which is directly an outcome of energy balance. Why? Because it is operating in a cyclic process. So, if you write the first law, this is dE plus del W, and if I go for a cyclic integral, right. So, this becomes mod QH, this is 0, and this becomes mod W. Because heat and work, they are path functions. So, even if the original state is being regained, there will be some work and there will be some heat interaction with the surrounding. However, the energy, which is a combination of kinetic potential and internal energy, as we have discussed in previous lectures. So, that will be 0 if we perform a cyclic integral on it, okay, because its initial and final state are they are identical. So, with in relation to this energy balance, now it is important, see from this is first law, and from first law paradigm it is quite obvious that we write mod QH equal to mod W, right, mod QH equal to mod W. However, you see that mod QH is not the term actually, right. If it is a cyclic process, we have to write mod QH minus mod QC is equal to mod W. So, in general, if we forget about the second law and start writing this for this type of schematic, right, and where we do not know whether it is operating in a cyclic or acyclic process, so you can directly write it. So, mod QH equal to mod W, what we were talking about, that conversion of work into or conversion of heat into work, fully it is possible with 100% efficiency. However, the second law actually justifies that if it is operating in a cyclic process, this mod QC can never be 0 provided that mod QH and mod W are not equal to 0. So, mod QH minus mod QC equal to the net work performed by the system, which is del W, and which is alternatively the del W produced minus del W, or this W produced minus W intake, right. So, from here we can define this performance rating parameter efficiency, that is mod W by mod QH. Now, mod W, you see it is mod QH minus mod QC divided by mod QH. So, efficiency, even if we want to eliminate this work term, we can use this energy balance and we can write that 1 minus mod QC by mod QH, right. So, this is the alternative definition, this is the fundamental definition, okay, and this is the typical combination of simple energy balance with respect to this basic or the fundamental definition of efficiency. So, that is the idea of heat engine. See, we can think like we have a high temperature object, we have a low temperature object, and we have another working medium, right, gas in piston cylinder assembly. Now, these walls are the side walls we can consider they are perfect insulator. This is a thought experiment basically, and this is a perfect conductor, right. Now, if I put it here, there will be heat intake, if I put it here, there will be heat rejection, and additionally if it is not a two-step process like heat input and heat rejection, right. Additionally, we can think of the insulated stand, right, where we can exhibit some adiabatic process. So, that may be needed. However, you see in complex, this is the simplest structure of heat engine. We can think of heat engines additionally where this TH is going to change, right. It is not a constant temperature heat engine, it may be a heat engine where the temperature changes, right, even during the heat input step, but these are secondary, these heat engines are non-primary type. The primary one requires only this in its elementary construction. One high temperature reservoir or high temp, not object, let us write reservoir, low temperature reservoir, and an insulating stand. That is sufficient to think of the elementary structure of a heat engine, right. So, once we have completed the discussion, elementary discussion or the beginning discussion of the heat engine, let's think what is a refrigerator, because that concept is equivalent to heat engine from the perspective of Clausius statement. Refrigerator, alternatively it may be a heat pump, right. So what is the difference? Both the structures are same, the schematic at least they are same, however the objectives are different. In refrigerator, our objective is to keep a low temperature, the objective is at the expense of work we have to abstract heat from the low temperature reservoir, that is the objective. How much we are abstracting, based on that we will do some performance rating. Whereas in high temperature reservoir, or sorry, in this case of heat pump, our objective is to keep this high temperature reservoir at the elevated level, right. So there the objective will be how much heat we are delivering. So in refrigerator, you see important for refrigerator, or primarily important rather, primary target variable for refrigerator, and this is the primary target variable for heat pump, right. So what the heat engine or heat pump consists of? The same two reservoirs, one is at high temperature, another is at low temperature, and intermediately we will have the working medium, right. So this also consists of two reservoirs, one is at high temperature, another is at low temperature. So what is the schematic? Schematic remains the same, right. However, the direction of the arrows will change. So refrigerator or heat pump, the schematic is something like this. R or HP. Here we are taking up QC, delivering QH, and this work we are giving as input to this working medium. So Clausius statement is if mod QC or mod QH are not equal to 0, then mod W, or it's positive, then mod W is positive, right. So this is the Clausius statement basically, okay. So you see that here we can write efficiency equivalent term as my input. What is the input? What is must be the input. And what is the output? For refrigerator the output is QC, for heat pump the output is QH. So we write mod QC by mod W, right, or efficiency of this refrigerator and efficiency of this heat pump we can write mod QH divided by mod W. Now you see that mod QH, from energy balance we can get that mod QH is always greater than mod W, and here mod QC may be greater or less than mod W, we do not know. So in both of the cases this term becomes greater than 1 and violates the conventional understanding or the notion about efficiency, right. So we will not call them efficiency, but we rather call them as coefficient of performance, because classically the efficiency should be less than 1, okay. So coefficient of performance for refrigerator is mod QC divided by mod QH minus mod QC, which is an outcome of energy balance. and coefficient of performance for heat pump, it is mod QH divided by mod QH minus mod QC, and this is going to be 1 minus respective efficiency of heat engine. Because heat engines, if we just revert the arrows, it becomes a heat engine, and for heat engine this efficiency will be 1 minus mod QC by mod QH, that we have justified and proved, right. So, here the equivalent heat pump will have the coefficient of performance which is inverse of this efficiency of the corresponding heat engine. So, that is the basic idea of heat engine and refrigerator. So, with that understanding, now we will try to go for the simplest arrangement, the elementary structure with the simplest arrangement for heat engine, giving me what should be the process, right. Like what process will be executed if I have to go for the highest efficiency for the heat engine. So, we have, so what is the problem? Problem statement, we have an elementary or the simplest heat engine, right. It consists of two thermal reservoirs of constant temperature and the working medium. Right. So, we have the elementary or the simplest heat engine, just like this. Okay. What should be the design of the cyclic process in order to have highest efficiency, right. And that was answered by Nicholas Leonard Sadi Carnot in 1824, something like that. Yes, 1824, and the title of the monogram was Reflection on the Motive Power of Heat, right. So, in this monogram, he answered the question that when or what should be the sequence of these processes in order to extract maximum efficiency from an elementary heat engine, which consists of two constant temperature reservoir and the working medium, right. And he was only at that time in 1824, he was around 18 years, right. And in his monograph, he established that it must be a reversible cycle, right. Whatever the processes are, it must be a reversible cycle, right. Why reversible? Because maximally efficient. Reversible processes are maximally efficient. We know no matter whether it is a work producing step or work absorbing step, it must be maximally efficient. In order to have this maximal efficiency, each and every step of this process must be reversible. Now, the obvious question that we all know Carnot cycle, right? The obvious question is, okay, we can understand that, okay, it must be reversible. But why it is first adiabatic expansion or heat input, sorry, isothermal expansion or heat input, then adiabatic expansion followed by isothermal heat rejection and adiabatic compression to the initial state, right? Why it is so? Why it cannot be an isobaric heat input, then isochoric expansion, then again another isobaric heat rejection and isochoric return to that initial state? Why it is not like that? Okay. So, here the problem is, or the answer is inbuilt in this statement of reversibility and this construction. So, we will try to understand it. See, in PV space, because why we have chosen PV space? Homogeneous and single phase working material. So, degrees of freedom is 2. So, the dimensionality of the phase space is 2, right? And we choose pressure and volume to have a physical feel about that process, but theoretically it should be pressure and temperature. But we do not go for understanding, we do not go for the use of this pressure temperature phase plot or phase diagram, because we want to understand the process. And once it is volume, though it is not a canonical variable, in terms of volume we can understand the process better rather than pressure and temperature. So, you see reversibility. First we have to go for a reversible heat input step, because we have a high temperature reservoir. Now, when the process heat input, or rather reversible heat input, how come it is possible? If and only if this source and working material gas and source must have the same temperature. Why? Because same temperature, exactly it will not be same temperature. Here if it is TH, here it should be TH minus DTH. Differentially small, and which we can consider to be same, right? So, the source temperature and the gas temperature must be same, which means the driving force is 0, and then we can actually implement the condition of reversible heat transfer, right, with constant temperature source. Remember that if I want to think that I want to go for an isobaric process or isobaric heat input, that is also possible. However, to implement this reversible isobaric heat input, we must go on changing the source temperature according to a pre-decided locus. That means it must be a programmed source where the temperature goes on changing, right? And the system also, it's at the same temperature as that of the source, but the source temperature is changing, and then only we can at least theoretically we can implement this reversible isobaric heat input step. However, here in this elementary structure we have a constant temperature thermal reservoir, and with that constant temperature thermal reservoir, if I have to implement a reversible heat input step, then it must be isothermal. There is no other option. So, the heat input step is isothermal. Let us say it is from state 1 to state 2. We are allowing it up to state 2. We could have allowed it to some further, but that is not the point. It is not a specific point. Here we stopped, right. Next, From here, again by an isothermal process, we cannot reject the heat, and we have to reject the heat to a low temperature reservoir. So you have to reduce the temperature of that system, and we don't have anything else except an insulated stand. So we'll put it here, and we'll allow the medium to expand further, right? Which means we have to go for an adiabatic expansion, which we will allow unless and until the temperature of this working medium drops same as that of the temperature of the sink. Why? Because next step will be the heat rejection, and that heat rejection, in order to implement this reversibility, again should have zero driving force. That means the system temperature and the sink temperature, right, must be same. Now the sink temperature is fixed, which is Tc. So we have to reduce the system temperature to Tc. Okay? So the next step is adiabatic expansion to the state 3, where the temperature, here the temperature is Th throughout the process. Here the temperature will be Tc, right? So here we can implement this reversible heat rejection at Tc. Now again, if you think that okay, we will implement some isochoric pressure reduction, right? But isochoric pressure reduction means there will be some exchange of heat with some another object whose temperature is also to be programmed, right? So, and we don't have it as a utility or resource. So, we have to go for adiabatic process. So, that is why these individual steps, because of this constraint of reversibilities, are fixed, and they are also fixed because of my limitation in utility. I have a high temperature reservoir with constant temperature, low temperature reservoir again with constant temperature, and an insulated stand, nothing else. Okay? So, if I have to implement with this limited these utilities, if I have to implement reversibility, I have to go first for an isothermal expansion, then an adiabatic expansion, then isothermal compression, and we will continue it to some state 4, such that if I draw an adiabatic line through 1, it must intersect or it must pass through the point 4, right. So, this is point 4, and we have to regain this state. So, definitely we have to regain the state, and regaining it's only possible by isothermal compression. So, once it has rejected the heat to this low temperature reservoir, we are actually compressing. How it will reject? We are compressing it. We have to do work on that, right. So, we will put it here, we will do some external work, and the heat will be rejected. So, it is an isothermal this heat rejection step, and after that it will continue it to a fixed in final point 4, and once this point 4, it is to be pre-calculated. Once this point 4 is reached, we will again put it to the insulated stand, again do some work such that the initial state is regained. Okay. So, this is the reason that why the Carnot cycle has got this heat input, right, isothermal heat input or expansion, then adiabatic expansion, isothermal compression, and again followed by adiabatic compression. So, these are fixed and universal. We cannot implement anything else with this limited resource and with the constraint of reversibility. So, this is Carnot cycle, right. This is Carnot cycle, and we can trace the curve because it is reversible process or reversible cycle in general, right. So, with this reversible cycle, here we are going to prove this Carnot cycle efficiency to be 1 minus Tc by Th, and as we are not introduced to this concept of entropy, here we have to consider some working material, and that will be ideal gas. However, the Carnot cycle, its efficiency is universal. Even if we drop, we will see later when this concept of entropy is being introduced, then we can prove this efficiency to remain invariant, what we are going to prove here with this assumption of ideal gas. So, you see that eta is 1 minus mod of QC by mod of QH, right. So, mod of QH, it is nRTH into ln of V2 by V1, and mod of QC, it's equal to nRTC ln of V3 by V4. It should not be V4 by V3. Why? Because you see, this V4 is the final state, V3 3 is the initial state. So, truly we should write this work as V4 by V3. However, here we are writing as V3 by V4. The reason is actually QC will have a negative sign for this process. So, as we are putting a mod, we should go for checking whether the logarithmic term is also positive or not, because here we are not putting any mod sign. So, evidently here we are not putting any mod sign. So, definitely it should be higher divided by the lower and the logarithm of that. Okay. So, 1 minus, or efficiency rather, efficiency expression, it is 1 minus Tc by Th into ln of V3 by V4 divided by ln of V2 by V1. Now, we can further simplify it if I apply the reversibility in this, or reversibility condition for ideal gas in these adiabatic steps, right. So, for 2 to 3, we can write this Th into V2 to the power gamma minus 1 is equal to Tc into V3 to the power gamma minus 1. So, V2 by V3 equal to Tc by Th to the power 1 by gamma minus 1, right. And similarly, for 4 to 1, Tc into V4 to the power gamma minus 1 is equal to Th into V1 to the power gamma minus 1. So, V4 by V1, here is Tc by Th. So, V1 by V4 is equal to Tc divided by Th to the power 1 divided by gamma minus 1. So, essentially this V2 by V3 equal to V1 by V4. V2 by V3 equal to V1 by V4. So, from there we can establish that V3 by V4 is equal to V3 by V4 is equal to V2 by V1. So, these two terms, these two logarithmic terms, they cancel out, and we can establish that 1 minus Tc by Th is the final expression of Carnot cycle efficiency, right. So, you see that this is the universal expression of Carnot cycle efficiency, and actually it is independent of the working material. We will prove it, and here with this scope, limited scope, we cannot prove it in PV space. Once we go for introducing the definition of entropy, then we can establish that actually that expression and the Carnot cycle performance is independent of the working material. We do not have to go by ideal gas. We will prove it later, but here we have to think of certain limiting value, right. See this power generation, we practice it in thermal power station majorly in large scale, right. And there we have the working material as water, which changes its state to superheated steam, then it expands to a turbine, and then there is a condenser and all, right. So, where we can implement, theoretically at least, we can implement the steps of this isothermal, though it is not at all theoretically feasible, this isothermal heat input, then adiabatic expansion, then isothermal heat rejection and adiabatic compression. So, what is the maximum possible theoretical efficiency what we can achieve at least, or that is a limiting value, right. And we can check the performance of real life power plant in a sense that what is its exact or actual efficiency. So, you see that what is the maximum possible efficiency. Now, Th, you see it is limited to 650 degrees Celsius, which is 650 plus 273 Kelvin, right. Why it is limited to 650? Because in boiler, actually boiler is this step where we deliver heat from the fossil fuels, okay. So it converts the subcooled water to superheated steam. Though it is not exactly this isothermal, but if I think of isothermal analog in this theoretical paradigm, it may be a saturated water which we are converting to saturated steam. So we can implement actually Carnot cycle. So there are definitely limitations and the technical problems. So even if we do that, at least in theory, so the maximum possible temperature is limited to 650 around, right. Why? Because at this 650 degree or 700 degree around, the pressure of water or the steam is around 10,000 kilopascal, right. And this conversion of water into steam is taking place within the boiler tubes. Now, boiler tube has got a limited specific thickness. We cannot go on increasing it indefinitely, because from the heat there are heat transfer perspective. As we are increasing the thickness, definitely what will happen? Its heat transfer resistance will increase and the process will be infinitely delayed. So there must be a finite thickness. So within this finite thickness, if we go for using the high performance metal as boiler tube material, then generally it is the thumb rule that we should not go beyond a pressure of 10,000 kilopascal, right, or sorry 10,000 pascal. So the maximum temperature we limit it for working material as water to 650, right. Now the temperature of the sink, which is same as that of this atmosphere, is around 300 Kelvin, right. So you see 650 plus 273, how much it is? 3, 12, 9. So approximately it is in the order of 900 Kelvin, if we think it, right, and this is 300 Kelvin. So efficiency maximum possible is 300 divided by 900, so it is 0.66, right, 66% maximally, okay, with Carnot cycle. It is a theoretical limit. So what is the actual efficiency of power plants? Around 35, 38, something like that, okay. So it is nearly half or more than half of this Carnot cycle, respective Carnot cycle efficiency, because we can, in reality, we can never implement a reversible process, okay. So that's all about the Carnot cycle. Now you see, very similar to this Carnot cycle, we can think of Carnot refrigerator and Carnot heat engine, just the same process in a reverse direction, right. So in this, that is an isothermal heat input, then adiabatic compression, isothermal this heat rejection and adiabatic expansion. So we can implement a reversible Carnot cycle in the reverse direction, right. So reversible Carnot cycle in opposite direction, or Carnot heat engine in opposite direction, give rise to Carnot refrigerator or heat pump. And what will be the coefficient of performance of a Carnot refrigerator? It will be 1 minus, as we have seen, that sorry, mod QC divided by mod QH minus mod QC. So it's automatically here, you can understand that here we are getting a very important equation, that mod QC by mod QH is basically TC by TH. So we can write it as TH divided by TH minus TC, and coefficient of performance for a Carnot heat pump, it's equal to, formal definition is QH mod QH by mod QH minus mod QC. So, it is equal to TH divided by TH minus TC. It is equal to Carnot cycle efficiency, right, as heat engine. So, as it is reversible, so definitely the Carnot cycle will be having the highest efficiency, but at the same time it is a theoretical possibility because we cannot implement this reversible process, right. So, this leads to this Carnot theorem. Definitely it is of theoretical importance. What are they? Carnot theorem 1, two Carnot theorems. No heat engine operating between two given thermal reservoirs with fixed temperature can be more efficient than a reversible engine operating between the same reservoirs. We have seen that there is no other feasibility of proposing any alternative process than the Carnot cycle if I have to implement the reversible cycle. And Carnot theorem 2, all reversible engines operating between the same two given thermal reservoirs with fixed temperature have same efficiency, as we have seen. So, these two are basically same or equivalent statement, this Carnot theorem 1 and Carnot theorem 2. And with this idea of this Carnot cycle efficiency and specifically with this concept of this equation mod QC by mod QH is equal to TC by TH for a Carnot cycle. Next, in the next session, we will try to generalize this concept of a Carnot cycle to any reversible cycle, definitely with multiple reservoirs or programmed temperature reservoirs, right. For reversible cycle, how this QC by QH, this term actually looks like, okay. So, that we will be trying to prove, because here from this equation what we see, this mod QC divided by TC is equal to mod QH divided by TH. Now, from the perspective of heat engine, you see that we have to write this mod QC as minus of QC, because QC and QH are with respect to, or we are defining it with respect to the working medium. So, QC is actually heat rejection, so it is negative, so minus of QC is positive, so it is matching with mod QC divided by TC, but here it is same because it is the heat input, QH divided by TH. So, what we can write? QH divided by TH plus QC divided by TC is equal to 0. So, these are the two heat interaction terms. So, del Q divided by T equal to 0 for a Carnot cycle. Right. So, in the next session, first we are going to prove that this equality will hold for all reversible cycle and the sign will change to negative. This will no longer be equality if it is an irreversible cycle. And combined, we can establish that del Q divided by T is less than equal to 0 universally, no matter whether it is reversible or irreversible. If it is reversible, it will be equal to 0. If it is irreversible, it will be less than 0, and that statement we call as Clausius inequality, which we are going to establish and discuss in the next session. Thank you.